Thank you, everyone. And today we have the second part of the session about the entropic associative memory by the architecture developed by Professor Pineda and his team. So last week he gave a very intuitive explanation of the theory behind the framework. And today he's going to go and explain more into detail the experiments and the results. So Professor Pineda, the stage is yours.
Thank you very much. Well, thanks again, Tom, for the invitation and Tesh for coordinating the event. And as you said, today I'll talk about this architecture of the system and the experiments and results. And I go straight to the presentation. Here. Can you see it okay?
Yes.
Right. So, well, the first thing I like to stress is that we presuppose a three-layer cognitive architecture with a primary zone or concrete representations that are modal, specific to the kind of modality, modal image that may be images or maybe sound, speech, or other kinds of modalities, as long as they are local and they are of a concrete nature. And then there is a second level of representations which are abstract, in the sense that the features of these representations do not correspond to objects in the particular modality, which are just already very general, have no particular interpretation, but nevertheless are local. So this is a kind of secondary zone or level. But the important key here is that the local modality specific representations stand in a one-to-one relation with the abstract representations. And then there is a third level in which there are abstract and distributed representations. And this is the level in which the information is stored in memory. And here there is an end-to-end relation between the representations in this level and the third level that are fully distributed and the representations in the second level. And for perception, these representations are constructed bottom-up from the primary to the secondary to the third level, in a way, so this have this incoming path. And for generation or motor action, they go to the reverse path in a symmetrical way. Now, this can be pictured as well in terms of an architecture that is a computational architecture, right? That is the one we are using for the experiments, so a simulation of this one, in which the first representation, the primary representations are in modal buffers that are fed directly from the environment and are related directly to the final architecture of the system. And these representations, for instance, are the pixels in an image, okay? And these objects are directly the input to the analysis module, which kind of the bottom-up part of the perceptual module that transforms these concrete representations into another set of abstract representation in this level that are placed so-called in the structure bus in between. And here are the second level representations. And on the way out, these intermediate representations are synthesized by a action module and transformed from the abstract to the local models, and then from there are the images that are rendered on the screen, or you can think of it as the motor structure for some particular modality. And then at the third level, we have the actual memory the associative memory registers. There are a number of memory registers. Each one has an auxiliary register through which the input and output information is placed, and these are all hanging on the bus. Right? And so this is the third level architecture where the representations are already fully distributed. For the lambda register operation, the information goes all the way from the observation into the input model, and then is transformed in the abstract representation, and then there is a designated register in which the information is input. And then when this operation is taking place, all the other registers are inhibited, so they are out. So this is a control supervised register of the information, and of course we presuppose that there's a kind of attention and control mechanism that so already addresses the memory to the right register. In the case of the recognition operation, the queue goes through from the external world to the input buffer to the analysis model, and then the queue is placed in this bus, in the second structure, and then all of the registers are queried because anyone is a candidate for recognition, but only one, well, possibly more, respond. And when this respond, is because the queue successfully matches an object that is stored in the memory. And then for the Vida retrieval, this object is rendered back through the synthesis model and then through the model specific specific buffer and render into the outside world. Okay, so you can think of this, well, this is an actual computational architecture, but also you can think of it as the conceptual organization of the memory system in a kind of abstract way. Now, these modules are implemented through what is called an autoencoder, that you can look at this here. So this pixel buffer corresponds to the input modality, which is a specific, and then there are features. In this case, this 784 corresponds, there are images of 28 times 28 pixels, and then with 256 values, and then these are the features, all the pixels, and here there are the integer values of each pixel, which are the input to a 3 layers convolutional neural network, which is an encoder. Okay, and this maps this information into another feature set, which is a compressed set, in this case, 64 features, which corresponds to the columns of the associative memory registers, or in the abstract representations, these are the arguments of the function that are represented in the memory. And of course, these have real values, but then when they are input into the memory, they are quantized, normalized, and fill as marks in the memories, corresponding memory cells. Okay, so the information that goes into the bus is here. These are the 64 features, and you can think that this bus has these 64 lines that feed directly into the registers. And then for the output, there is a two-transpose convolutional network that maps the abstract representation in this feature space to the actual image again. So this feature corresponds to the image, to the pixels, and then the images are constructed, are generated back through here. And the architecture also has a classifier, that's an auxiliary model that is built with two fully connected layer neural network that classifies, in this case, for the case of the digits, the classes of each digit, and this helps to assess the performance of the decoder. And all these modules are trained together at the same time. So the images with the corresponding digits are here also are the images. And this module corresponds to the analysis module, the perceptual component, and this decoder corresponds to the synthesis module, that is the one who renders the complete representations out of the abstract representations. Okay, so now we did this first experiment of the memory using the MNIST corpus of manuscript digits, which has 70,000 instances of digits. And these were the things that were stored in the memory and had to be subject to recognition and to regeneration. And from this set, we used 70% of the corpus just for training the analysis and synthesis models. That is the autoencode. So there was a designated set that was just used for that purpose. And then we had 33% to be used as remembering corpus. So the actual information that is going to be input or registered into the associative memory register. And of course, these sets are different and mutually exclusive. And the remaining 10% was just used for testing the performance of the memory at a particular stage of information with some particular synthesis and analysis models. So here then we run a number of experiments. The first was used to determine the size and the entropy range for the associative memory registers in the domain. So we needed to find exactly what was the size. We already had for preliminary experiments that the columns were going to be 64. I mean, these are large enough register, and they present the domain of the function that we're going to be stored, and it's already a pretty big object. But nevertheless, as the information stored in these cells are just blanks or marks, it's just one bit of information, and this register of 64, well, are rational. But we didn't know exactly how many rows do we need to have in order to have an acceptable performance of the register. And of course, the larger the number of rows, the larger the register, and also hardest to represent the information is, as we are going to see now. Now, the second experiment was performed with the purpose to see whether we could have two different classes of objects stored in the same register. And this is essential in order to make associations, because from information of one class to another. And the point is whether we could register information of two different classes and nevertheless have an acceptable performance in recognition and retribution of objects of the class. And when we had this done, so we had kind of configured an operational system. We know that we have these registers that were operational with us certain parameters of performance. And then the third experiment was, now that we had this, well, let's go into put information into the memory, and then we are going to assess what is the precision and recall of the recognition and retrieval operation, having a different amount of information stored in the register, from very, very few information to very, very large amounts of information. And that is to say, how these operations perform at different entropy levels. And now when was that done, the fourth experiment had to do with, now we're going to recover objects. So with queues at different levels of entropy, we're going to get objects and render them back from the memory. And finally, the fifth experiment consisted in do that, but having incomplete information. In particular, in this experiment, we have the object, the queues, that were very significantly occluded So the information that was available for the operation was pretty much diminished. And we want to see how this performs, when the memory performs with this limited amount of information. So the experiment one. So as we were recovering the digits, there are 10 digits. So we define one associative memory register for each digit. Okay, so we had 10 digits. And the point is, we train the networks in order to render these representations, and we store objects of the corresponding class in the corresponding registers. And here we can see, so the purpose of this is to determine the size of the registers. So, and this figure shows in the horizontal axis the number of rows of the register. In this case, we already chose that the columns are going to be 64 columns, registers of 64 columns. But we had to see, I mean, what happened with different numbers of rows, and we tried with the integral powers of 2, one row, 2 rows, 4 rows, 8 rows, 16, 32, 64, 128, 266, and 50, 512. Okay, and then on the vertical axis we have the performance, which is the blue graph is the recall, and the red one is the precision. Okay, with the numbers of rows, with the standard recall or precision formula. So the precision is the true positives divided by the true positives plus the false positives, and the recall is the true positives divided by the true positives plus the true negatives. And
so, sorry, Luis, just to clarify, the performance here is just with respect to the test data, right?
The test data, yes, performance in relation to the
unseen data.
Unseen data, and yeah, the registers are filled up with the remember corpus. Okay, that is a different partition. Okay, so as you can see here, when we have just one row, well, everything is accepted. So recollection is 100% because it's just one row on the table. But the precision is just 1% because there's 10% of data corresponding to that particular class. That's expected. Okay, but then very quickly, with 2 rows, the precision goes significantly up. The recall remains high, and this tendency goes to 16 rows, which actually the precision is pretty high, and the precision is still high. And then 54, 52 is probably the best trade-off between the two. And from this on, the precision continues to keep on. So whenever something is tested, it is recovered precisely, but the recall goes down because the grid is starting.
Sorry, can I interrupt one more time? Can you just go back where you had like the breakdown of the data set to the different portions and percentages of, yes, this one. So can you explain again, like how the test corpus is being used? Because, you know, in your figures right now, you're comparing the performance against, you know, the recall and the precision of the recall. But I assume that applies to the training corpus and the remembering, right?
Yeah, so I mean, this 50% is just for training the networks. I mean, the analysis and synthesis network. So it's a partition.
Okay.
And this one, 53%, I mean, the corpus is balanced, so there are more or less the same number of instances for each class. And this is the information that is used to fill up the memory, each memories. And this 10% is this corpus that was kept apart, that is used to test whether it's recalled in the corresponding memory registers. Can be used as a cue to recover an object. Okay.
Okay, so so it's not that it's not like episodic memory in which you're asking it to recall the same instance. You're saying it can be a different instance, but it has to recall the same category. Is that how?
Yeah. Well, yes, we're going to discuss that because the thing is, well, it is going to be clear later on when I show you the actual recollection of objects. But I remember from the last session, that the queue selects an object, but the object that is recalled is a reconstruction always. Okay, see, and that reconstruction has a random parameter in order to be recovered. Okay, so it's not only a classification, but it's a reconstruction. And here at the moment, I'm just checking, I'm testing the performance of the recognition operation. Okay, and you can think of it as a classifier at this particular point.
Okay, all right, okay. Thanks. Yeah.
So as you see, the precision goes up pretty quickly, and then stays up, and the recall starts to decrease when the grid becomes too fine. And this is because as the grid is too fine, you can think that the Q might point to a particular square, but as the square is too fine, it must just have near misses, and then it's very difficult to get exactly the value of the cell, and then that's the reason this is being recalled. So these are false positives. Okay, so that's why this recall drops. And then the table on the right is the performance, but not at the level of each individual memory register, but it's at the system as a whole. And in this case, if the AQ is rejected by the 10 registers, that can happen, then that's a false positive, it's a false negative for the whole memory system. Acts for the register that accepts, and a false positive and a false negative for the right class. So then when we have this performance, then you see that the precision and the recall grow more or less at the same rate. And at the end, we have a reasonable performance of the system as a whole. Okay. And what there is a range of memory in which there's a good compromise. And as you see here at the bottom, this is the entropy that is associated with the number of the size of the grid. Okay, here. Now this graphing here represents how many register response with a given size or number of rows. And for instance, if there is one row, all the registers, the 10 registers respond because it's, but of course we know that there are false positive. But then we had to row, they're just a little above the 3 memory recall. And then when we get to about 52 or 16 register, only 1 register recall. So it's very good at rejecting the information that is not of the right class very quickly. I mean, with the grid is reasonably small. Okay. And this is another look of this graph in terms of the blue ones are the correct response chosen. The orange ones are the correct response is not chosen. The red ones is not response, and there is the green one that not correct response. So more or less, this is another look of this figure. Okay, so from this graph, we can see that register size 32 and 64 have a reasonable performance and for one class. So it was good news for us. And then in the experiment 2, instead of using 10 registers, we just use just 5 registers and place 2 arbitrary digits in each one register. So the idea is that there are the individual representations of a large number of instances in each register, but also of 2 different classes. And then the point is whether with a queue we can recover the right one in a reasonable way. And there's a lot of experiments were analogous completely to the first one, with the other difference that the entropies are higher. So we have a higher entropy. And of course, this is a higher entropy because we have the registers have twice as many instances of 2 different classes in each register, what we would expect is exactly that the entropy is increased. And it's exactly what happens. But the precision and the recall, both at the level of the memories, individual memories, and at the level of the system as a whole, perform more or less in the same way. So this was also good news. Okay. So the third experiment, I mean, we already knew that we had these registers of size 64 columns and 64 rows that were good, that respond reasonably. And then what we did is to investigate in this register what happened. We test the recognition, but with different amounts of information stored in the register. So in this case, the horizontal axis represents how much information of the memory corpus, of the remembered corpus, is actually feeding into the registers. So in this case, it's just 1%. Okay, so you can imagine that there is this register, and then we feed only 1% of the information. So it's a pretty spare register. It has very little on it. Okay. The memory is like a container. Okay. And the more information this container is, more filled up and has more information. So this is what represented here. So we have 1%, 2%, 4%, 8, 16, 32, 64%, and then 10% is the full of the 100% of the remembered corpus. And what we have in this line is the actual entropy. So as there's more information, then the entropy in the register is increased. And then we test what happened when we recall information. So we give a cue. So in this, as you can see, precision keeps always very high in this setting. Okay, it's because when the information with the cue actually selects an object, it's very likely that is the right object or object of the same class. Okay, but if there is very little information, there are few objects in the memory, and most of the cues are going to be rejected, even if they are of the same class, the right class. Okay, so the point is that the recall started to increase when there is enough information in the memory, so there is a reasonable chance that a cue is actually going to be accepted. Okay, so and you can see here the memory trade-off I was talking about. If the entropy is very low and a cue is accepted, it's going to be very precise. But there are going to be a lot of cues of the right kind that are going to be rejected because there is no information in the memory. But there is a range of entropies in which there is a very good chance that when you have a cue of the right class, the memory is going to be dense enough, so you are going to get an object and it's going to be of the right class. Okay. But then when the memory...
Can I just try to rephrase what you just said there? So are you saying that adding the entropy makes recall easier because some of the differences don't matter or something like that? So, you know, if you're looking at exact matches, if you're looking for exact matches, then, you know, rejection will be easy, right? But if there's some ambiguity, then, you know, matching will become easier. Would that be one way of saying it, or?
Well, I mean, that's one of the conclusions I'm going to say. I mean, because when the entropy is high, I mean, the memory is kind of, they are going to be, well, the matches are going to be there because the memory is more dense. So there is more information, right? So when we register information, we register individual functions, the individual cues. But you remember that I talked about this productivity of the memory, that the actual functions that there are 2 to the power of the entropy times the number of arguments. And this is a huge amount of numbers that are there. So as a side effect of registering information, just by the interactions of the objects that are registered, there are other potential objects that are there. The number of functions is much larger. There are potentially objects of the same class, and the memory is more dense. Okay. So this is the effect of the the gain of the distributed representation.
Yeah. So that's so. Do you have a more, let's say, have you looked at why that is the case? Like, you know, what is it about the effect of the interaction or overlap between the memories that you know, makes these results show up the way that you're showing it here? Of
I'm going to show some visual except with the, and then we can come back to this point if you like.
All right.
Okay, so now in this fourth experiment, we're going to see how do this object look? I mean, when we have a cube and recover an object, what do this object look with different levels of entropy? And for this, I mean, we had three settings. In the first one, we retrieve objects when the entropy of the memory is very low. Okay. So as this is very low, I mean, it's likely that the queue has to be very similar to the object, that it kind of be close to photographic images. But on the other hand, the entropy is very low, I mean, and the queue is accepted, then it is likely that the same queue is going to be accepted at higher levels, all the way down, because the information is already there. This is the first setting. And the second setting, we use queues that are accepted and some moderate level of entropy, but are rejected at very low entropies. Okay. So these are kind of harder. Okay. And when the objects are going to be recovered, there's a space that for have a larger diversity in the shape of the recovered object. And then in the next case, we have we are going to select objects, queues that are only retrieved, accepted at high entropies, okay? But they are not accepted at lower entropies. So they are going to be much different. And finally, we are going to have objects that are rejected at all levels of entropy. And here we have some examples, this table. So this case, in the original image, this is the queue. These are the queue to the memory operation. And the second row are the image that is rendered through the autoencoder without recalling information to the memory. So the input is just mapping to the output, the word at the autoencoder. So in general, these are good. Okay, but remember that in this case, these queues are accepted at very low levels of entropy when the memory is pretty empty in general. And then, of course, as they are accepted at low levels of entropy, they are also accepted at higher levels. And in this case, they preserve good quality of the shapes. However, when the entropy starts to be larger, like 32% or 60%, which is the order of 3.2, 3.3, the quality of the object started to decrease because the fact of this reconstruction, the fact that we select an object randomly on the base of the queue and render the values of some of the arguments conforming or constructing a new object. So that happens all the time, I mean, in every case. But this reflects more inequality at the high entropies in which the quality object is reduced. Now, see what happens in this case. We have, again, in this image, we have the original queue, but that is not so good, okay? The quality of this queue is lower. And these queues, we selected for this table, queues that were accepted at some level of entropy, but were not accepted at lower entropies. So in this case, again, we have the original image, this is the queue, the decoded image, that is the image generated by the autoencoder. But then we see here that when the entropy is 1%, all queues are rejected. The memory says, I don't know you. You are not an object of this class. But then quickly enough, when the entropy starts to increase, there's more information and it gets easier to accept the queues. And for some objects start quickly Some others are harder. In this case, for instance, the 5 is accepted until very high entropies. And again, according to the entropy, the larger the entropy, the reconstruction is kind of a bit further away from the original object. But these are low quality objects. And then in this particular case, for this final example, we choose Qs that were rejected at all entropy levels. Okay, so they are digits, they are from the MNIST corpus, but they are not very good. They are, I mean, this calligraphic representation. And as you can see, well, the quality is much lower. This is barely a 2, and the 3 is pretty bad, and the 6 kind of a moon, and the 8 looks like a gamma, and the 9 looks an A. So it's what the people write, okay? And then the memory reject them all at all levels of entropy. So you are not good enough for me. Okay? But nevertheless, the autoencoder does produce something. So the encoder produces the actual representation, and this is mapped back and produces the actual representation. And there is always something out from the networks. But as you see, the answers are not necessarily of the right kind. So for instance, this 8 looks like a 7, and this 3 is barely a 3, etc. This 5 is a 6, and there's no way to tell. I mean, because the autoencoder said you are that, and although it's the right class, well, it's not the way to assess. Nevertheless, but the memory does reject that. Okay. So there's a very important difference between having a declarative memory and having a procedural memory. A declarative memory can reject objects that are not registered in the memory. And it does it directly. But a network doesn't do that. A network is a transfer function that maps always the input to the output, regardless whether the input are of the right kind. Okay, and then we go to the fifth experiment. And in this case, what we did is let's hide a large amount of information on the queue. And these are the figures, as you can see. So I don't know if you can see it, but in at the right side, in these figures, this is the queue. And this queue, half of the top half of the queue is blocked. So we have a blacks put on it. So the only thing that is visible is the lower half of the queue. So it's pretty hard. I mean, there is very little information. And then we recover these objects at different levels of entropy. In this case, in the first case, is no relaxation in the sense that we require that all 64 features of the queue had to be accepted in order that the queue is accepted. And then, and as you see, well, the precision is good, but lowers here, but the recall is pretty bad. And why is it pretty bad? Because there is very little information on the input, okay? And then as expected, most of the queues are rejected. Although there is a few objects that are constructed at very high entropies. But the networks, the autoencoder, the analysis and synthesis model, nevertheless do render something to reconstruct the information from these very, very lowly informative queues. But of course, these reconstructions might be pretty ambiguous or wrong, okay? So what the network does kind of produce the most a kind of prototype of the object of the class that is approximated by the queue somehow. But with not relaxation, well, most of the queues are excluded. So then we studied, I mean, for the objects, I mean, for the that were of the right class, I mean, what was the extensive features that fail in order that the object failed? And then we found that this was quite interesting, that there's with the little structure that is in the Q, I mean, most of the features have the right value, and there is a very, very few number of features that are not accepted, and that's the reason why these Qs are not accepted altogether. So what we did is to have a very simple relaxation technique, in which what we did is just to relax, and here in this case, instead of asking that the 64 features of the Q were accepted, we relaxed one feature. So we accepted this if 63 features were accepted. And then what it does is to increase the recall, because there's more, the test for accepting is less strict. And then as the recall was increased, then we have more reconstructions at high entropies. And then in this case, the third case, we relax, but now by 2 arguments. We require that 62 out of the 64 features were accepted, but we allowed that 2 were not accepted. And from this, we have a significant increase of the recall, and then was reflected in that most of the Qs render something back at high entropies. And in the last case, we further relax another argument. So we relax 3 arguments, and then this effect can be appreciated more effectively. So the moral of this experiment is that the Q, I mean, is incomplete because the conditions of observation, there are occlusions, maybe noise. I mean, a strong test might reject everything. But nevertheless, to have a Q is more useful to have as not having anything at all. Okay. And because a Q might be just later on interpreted in relation to a context, and then one might get a good hypothesis of what is there and resolve that. So this is the effect. So this setting, we run this setting with another something is going. Okay, and here, as you can see, the occlusion is different. In this case, we have bars on top of the Q, parallel bars. Instead of having a blockage of the top of the figure, we just place bars. Hidden more or less 50% of the figure in front of the Qs. And run the same experiment. And in this configuration, the effect is pretty similar. Oh, something happens with my computer.
Right, we're already 50 minutes into the seminar, Luis. Maybe you can give us a kind of summary.
Right. So I just mentioned very quickly that we run experiments also for letters.
Okay.
In the same sense. So here is now the MNIS corpus, and these are letters that are the Qs, letters and digits, and the Qs are accepted at very low entropy levels and perform more or less the same. And here, the Qs are accepted at moderate levels of entropy, but not at lower entropies. And then we have the same effect that are rejected at low entropies, but then accepted. And we have Qs that are accepted at only at very high levels of entropy or not accepted at all. Okay. and we have the same effect. So, just a quick recollection of the entropy and the entropy trade-off. I mean, when we input information into the memory, I mean, the memory gets more determined they are there. So, and the entropy in general lowers. But for recognition, I mean, we need to have a high entropy in order that the system is more able to attend the diversity of possible income stimuli. And then it's good for recognition that there is a high level in the memory. But on the other hand, for retrieval, we need to retrieve specific directed objects, and it's best for the system to retrieve objects, and this space kind of lowering the entropy. And these are the considerations we're using in the new version of the memory now. Okay, so with this, I just finished. I mean, with this, the entropic associative memory had these properties: associative, abstractive, constructive, distributive, declarative, and external negation. And also, I think, offers a reflection on constructivism versus associativism in learning. So this is clearly a constructivist approach in opposition to neural networks that model associations and reincarnate the associativism in a kind of sense. Okay, and I just finished with the paper that most of the material is in this paper that you see, and there's the second paper that is in the archive at the moment, is in revision, in which the experiments with letters and digits is explained, and also in this paper there is a long discussion about the difference between this declarative approach to memory in opposition to standard neural networks approaches, and in particular to coupled memory. There's a patent on this system that has already been granted, and there is a second patent that is in process at the moment. And the work in progress, I mean, now we are moving to more natural images, and there is work on phonetic memory with the DMX 100 corpus that we developed for phonetics of the Mexican Spanish. This is quite interesting, the work on this. And we are also working natural images of animals and artifacts, which the CIFAR corpus, which is the topic of Noé's here present doctoral dissertation. And we are also using the recognition of letters and digits for recognition handwriting text as an application of the system. That is the subject of one of the students doing his master's degrees at the moment, and there are other works planned for the future. I think with this I finished the exposition.
Thank you very much.
If you have any questions, I'll be happy to answer.
Thank you. Thank you very much. Yeah, so if anyone have a question, you can post it in the chat or raise your hand. In the meanwhile, okay, Tom, yes.
Thank you very much. There's a lot of information, and I think I'll take some time to properly digest and see how it relates with the kind of associative memory system that we're working on in our group. But one kind of like difference of emphasis that I see, and I just wanted to hear your opinion about it, is that so your system, you're interested in the different types of memory, and it's very interesting that you're combining the more the function of the declarative versus the more associative. But I also see an element of creativity in your system, which is because you're emphasizing the constructive aspect, and it's that aspect that I think relates more with our current work, where we're trying to see whether something like an updated Hopfield model with associative memory and entropy could serve as the platform for thinking about creativity in a very basic sense. What is it about creation of novelty in biological systems that could possibly be explained by this kind of work? So do you have any idea in your system maybe how you would incorporate ideas of imagination or novelty or creativity?
Well, yeah, there is one idea that kind of comes pretty clearly. I mean, and the way I think of it is this. I mean, the distributed representation generalizes.
Exactly.
So
Yeah.
we build a distributed representation with a given amount of information that is explicitly registered. And then from that, there are a number of potential units of information that can given as side effects for free. Okay, and this is this function that we computed. The amount of information in the memory at any particular state is 2 to the power of the entropy times the number of arguments. So it's a huge number. Okay, and this number is much, much larger than the number of objects that are actually registered explicitly. Okay, so we know that the objects that are registered somehow correspond to the reality. Okay, it's empirical experience that we are inputting into the system. But about this huge number of potential objects, we don't know they are potential, but we don't know whether they are real or not.
Exactly. Yeah.
Okay, and then, but we know they are potentially there. It's kind of innate knowledge in the original state. Okay.
Yeah. By the way, on this topic, I highly recommend if your group could read Busaki's recent book, The Brain from Inside Out. He's an EEG specialist, but in that book, he basically argues that the brain is organized in a kind of prefigured way, such that it has already a pre-built huge state space of possible attractors. And that what experience does is assign meaning to some of these attractors.
Right.
And so I think you will find it quite fitting for the kind of things that you're discussing right now.
Yeah, I think it's similar because the idea here is that when the system is interacting, the memory is interacting, the agent is interacting with the world, the memory is used to recognize and to build objects. Okay. But then when the objects, something is recognized in terms of this huge potential among this huge set of potential objects, then it means that that object that is image somehow becomes actual. Okay. And then becomes, and its synthesis, which is a construction, is kind of something that rendered by imagination, but it's a construction upon the given knowledge and upon the actual interaction with the environment. So it's kind of a way to enrich to specialize the knowledge. So I mean, so the original knowledge is kind of the original information, state of information is kind of small. Okay, the innate information, let's say, is some amount that is not being exposed to the environment, so it's not rich. Okay, but then with the experience, I mean, the world must enrich the information. Okay, but the memory system takes an active part in the objects that are interpreted become the objects that are likely to enrich the knowledge and also the productivity of the memory. So that is the kind of cycle that is involved in this.
Yeah, I like that way of thinking about things too. I think that's yeah, that it's kind of a different perspective from the kind of like just typical storehouse view of memory, right? But I think it's a much more fitting way of thinking about how real memory compared to, let's say, computer memory actually works.
Yeah, and that's clearly the difference to the standard computer memories, because first of all, I mean, computer memories are not associative. Memories are local.
Sure.
And a local memory has not this productivity associated or this generalization capability. Okay? It's kind of a passive object. Okay. Yeah. And it's what I said in the previous session, that the computer memories rather model external representations. I mean, the way we but they don't model the way the information is organized in a relational way. Okay, so in that sense, the idea of distributed representation that has a productivity is pretty important. Okay. But of course, I mean, if you implement a neural network with a standard computer that is digital, high RAM, I mean, at the end of the day, I mean, the distributed property is just simulated. It's not real because you are using an actual physical computer. So what I think is that, but you could also, I mean, of the brain, I mean, it's not implemented with a digital computer. I mean, the actual distributed representation is the actual machine, the brain, okay? And in that sense, I mean, the basic operations are quite different from the standard operations of digital computers of the standard kind. And I sustain and I support the idea that for this reason and many others, well, the brain is not a true machine.
Yes.
Okay.
There's
So
one thing that one final comment before I have to go and check on the kids, and then I'll pass it over back to Tesh. One thing that we're struggling with, and maybe also Tesh can also unpack this a little bit more, is that you know, it's a little bit difficult to conceive how to integrate this kind of system into a real-time sensory motor loop of an embodied agent interacting with the world. You know, because it's much easier to work with a system where we have full control of the timing of things and, like, you know, what's going to be presented and, you know, just checking like the recall. But to then go one step further and say, hey, we actually want to use this system, you know, to control an agent as it moves around the office space or something like that is a completely different kind of challenge. And I feel like, you know, looking at this in a decoupled way, like we're doing it right now, and also, you know, we're doing the same, but you know, going from a decoupled kind of system to a coupled system, then maybe it must still change somehow the way in which our architectures are designed. Would you agree with that, or do you think that you can just plug the system into a robot and without much change?
No, I mean, of course, I mean, I think there's a possibility to use this kind of memory in a robot, like Golem, for instance, a robot, but it could be kind of a limited increase of the functionality. Because in fact, I mean, not only memory, but also the other models of thinking and action must also sustain distributed representations of some kind. And function, thinking and planning and all that, I think can also be thought in terms of operations on this abstract space of distributed representations in a much more effective way. Okay. So in the program we are envisioning here, I mean, it is also possible to go from the architecture of the associative memory to architecture of rationality, in which more or less the input and output is more or less what is already sketched in the memory. But in addition to memory registers, there are thinking models that also hang on this bus, but implement transfer functions that are computed very effectively. Okay, and that may change the interaction with the world. Okay. Of course, I mean, with the stage of the technology and this theory, well, this is a long way away, but it would render a different way of interaction. I mean, but I think given the complexity of the natural agents and the environment, I mean, it has to go somehow that way. I mean, we have experimented long time for many years with robots like Golem, that performs the whole cycle: language, vision, thinking, knowledge, interact with the environment. It's very nice. I mean, it's beautiful. I mean, we are very proud of doing that. But nevertheless, we have to recognize that the functionality is very limited. And in fact, what happens with Golem and all service robots that we have at the moment is that they're designed to work in spaces where the entropy is pretty low. And that means that everything is quite predictable. Okay? And then they perform well. I mean, but this is
a good point, Luis. So I think that this is also maybe where I'm thinking about working with our system. So predictability is precisely it. So right now, it's a static system, right? You know, you present digits, you recall digits, and so what is being, you know, memorized and what's being recalled is an atemporal stimulus, right? It's a 2D array of pixels, let's say. So one of the things to think about in order to make this more, let's say, you know, interactive would be to say, how would the system work if the stimulus was actually, for example, a time series instead of like a 2D static array, you know? And then would it be possible to say, if I presented a certain kind of time series, it could actually predict into the future of how will this time series unfold next? and so give this a bit more of a predictive time-based component. And it's a little bit difficult to think about exactly how that would work, but I feel like if we implemented something like that, it would be much closer to something that we might want to even almost call cognitive already, that the system can generalize over time episodes of its past to predict what will be the unfolding of events, coming up next. And then, yeah. Go ahead.
It was a scenario thinking. I mean, one of the things we are doing in the case of speech is that the memory is used to interpret actual speech that is coming into the channel, okay? And then dynamically. And of course, I mean, we haven't done that predicting new speech that is going to come up. But nevertheless, yeah, the idea, I mean, the architecture is directed. I mean, so the agent is having this memory, but engaged with the environment, of course. So the point is that the point of the architecture is that the agent is engaged, and the operation of memory make that engagement pretty effective. I mean, so the memory helps to sustain a pretty tight loop with the environment.
Okay, very good, Luis. Thank you so much for your presentation and for answering my questions. So I have to put on my dad cap and do some house duties. So
thank you very much. Well, thank you for the invitation, and I hope it's been productive.
Yes, thank you so much. And we're going to keep a record of this also for students who are working in this area so that they can also check it out.
If you have any questions, you can write to us or talk to us in special sessions or whatever. We'd be interested in keeping on with this conversation.
Maybe we can get Tesh to give a presentation to your group at some point once we're a bit more advanced with our system. But I really have to go now. So thank you very much. Bye-bye.
See you. Thank you very much.
Thank you, Professor Pineda. It was very interesting. Yeah, actually, Tom pretty much asked everything I wanted to ask. And yes, I see there are no more questions. So it's possible to contact you.
Yes.
Yes. Okay. So we will then. I will record I will send you the links to the recordings, and we'll distribute it in our unit. And so if anybody has questions, I can give them your email and they can contact you.
Yes, we'll be very happy to talk to you and develop this.
Great. Thank you very much. And
thank you very much to you.
Have a good evening.
Okay, bye-bye.
Bye-bye.